Welcome to the Pod of Asclepius, your fortnightly healthcare technology podcast for the technical crowd. Sponsored by the American Statistical Association, we're bringing the technical experts of engineering, entrepreneurship, data science, and regulation straight to your earbuds. No fluff, no sale pitches, just important technical ideas described well to keep you up to date. All in the time it takes to get to work. And here's your host, Glenn Wright-Colopy.
Hey folks, welcome back to part 2 of our episode with Allison Meisner at Johns Hopkins University. In part 1, Allison discussed the interrelation between cardiac surgery and the risk of kidney failure in patients, and how doctors use prognostic models like hers to inform the clinical strategy for patients. She also talked about how her models assist in prognostic enrichment for trials. So not only is she good for doctors and patients, she's good for statisticians too. But the really cool thing about Allison's work is that many of us statisticians and engineers, we talk a lot about the importance of tailoring our work to the clinical application. But Allison actively pursues this by tuning her models specifically to the clinical objective and clinical constraints. And she's also created an R package to help other people do this as well. So in this part, we're going to go over the technical intuition and details of Allison's work. Allison has kindly provided us with slides, which are very helpful. So if you're listening on audio only, definitely keep listening, but also hop over to the YouTube channel to see us walk through the slides. If you're already watching from the YouTube, you're already in the perfect spot. Just kick back and enjoy the show. All right, Allison, I see that we have a really cool, colorful plot on slide 7. What do we need to know to get there?
Great, thank you. I'll first discuss some sort of terminology and abbreviations that are used in this area. So if we think of D as disease status, so 0 for people that don't have a disease and 1 if they do, and Z is a given biomarker combination, then we can define the true and false positive rate for a given threshold, which I call delta here. The true positive rate is simply the proportion of diseased individuals that have a biomarker value exceeding the threshold, and the false positive rate is the same among controls or non-diseased individuals. And then, as I mentioned earlier, in the first part, the receiver operating characteristic curve, or ROC curve, is simply a plot of the true positive rate versus the false positive rate as that threshold delta is varied. And then the area under the curve is simply the area under that ROC curve. So if you had a perfect biomarker, then that ROC curve would reach up to the top left corner of the unit square, and you would have an AUC of 1. If you had a useless biomarker, the ROC curve would fall on the diagonal, and you would have an AUC of 0.5. So as I mentioned before, there are lots of approaches that can be used to construct a combination. Things like likelihood-based methods, which are very common, as we talked about, like logistic regression is probably the number one choice for constructing a biomarker combination if you have a binary outcome. There are also things like fancy machine learning methods, support vector machines, classification trees, k-nearest neighbors. Generally, as we talked about in part 1, these might offer small gains in some data sets, but generally are not uniformly better than logistic regression or some of the methods I'll talk about here. And then the third set of methods that I also mentioned in part 1 are those targeting the area under the ROC curve. So that's the entire area, basically getting at the idea of if we're going to use this combination for prognosis, diagnosis, or screening, something where we would say we care about the AUC as a measure of sort of predictive capacity, then why not construct the combination by optimizing the AUC? So there's been a lot of work done on this, but what I would propose is that some investigators are not interested necessarily in the entire ROC curve, but rather are interested in specific false positive rate and would want a combination that optimizes the true positive rate for that false positive rate. So somebody might say, I can tolerate a false positive rate of 10%, so do the best you can within those confines. And that's what we're getting at. So to that end, we propose a distribution-free method for constructing biomarker combinations by maximizing the true positive rate while constraining the false positive rate at some user-specified level.
That's really interesting.
Thanks.
And also, just the way that you're using this, again, is presumably that the clinicians have identified, for example, that they can only handle certain throughput of false positives, or that they certainly have enough clinical time to investigate this many positive outcomes. Is that the idea behind them constructing these medically informed false positive constraints, and then you build your model to optimize performance while still meeting those requirements?
Exactly. And so depending upon the context, if having a positive test result would send you to have some massive intervention like a surgical procedure, we might only want to tolerate a very low false positive rate. We don't want to send too many people that don't need that surgical intervention to have it. If it's something like the intervention is we want you to exercise a bit more, or we want to see you twice a year instead of once a year, you might be willing to tolerate a higher false positive rate because you might be more willing to put controls through that intervention than you would have more serious intervention. So that's exactly it. So we're using our clinical knowledge of sort of how serious the disease, what sort of intervention will be proposed to people that are positive on the test, taking those factors into account and saying, okay, this is the false positive rate that I, from a clinical perspective, can tolerate. So yeah, the false positive rate comes from our clinical collaborators.
And just before we move on, you sort of hit on this point, but I thought it'd be nice to flesh it out a little bit more. There's also the issue that in medicine, we have sort of these unequal weighting between like risk tolerances. So we're willing to tolerate a certain type of risk or a certain type of poor performance, but we don't want it to drop below a certain level.
That's right. Yeah. So, and that's sort of one of the distinctions between if we're thinking about using this for screening versus diagnosis, those two situations we might be more or less willing to miss cases or be more concerned about avoiding picking up on controls. So exactly. So it's that trade-off of sensitivity and specificity.
Great. Let's move on.
Yeah, so then diving right into our proposed method. So we'll suppose that we have a set of P biomarkers that we denote as X, and we consider linear combinations defined by theta. Particularly, we define the true and false positive rate as functions of both the combination theta and then the threshold delta. So the true positive rate for a given combination theta and threshold delta is the proportion of diseased individuals whose combination exceeds the threshold, and the same for the false positive rate among non-diseased individuals. So what we're proposing is constructing a biomarker combination by maximizing the true positive rate while constraining the false positive rate at some level t. And so that's what's written here with this maximizer of the true positive rate over the set omega t, where omega t is simply the values of the combination and threshold such that the false positive rate is constrained at t. We also have to impose some normalization constraints, theta, so that it's identifiable, but it's not overly complicated. But the idea here is that we're optimizing the true positive rate over a set where we constrain the false positive rate. So, of course, in finite samples, we don't have the true and false positive rate. We have their empirical estimates, which are simply the sample averages of the number of non-diseased individuals and diseased individuals whose combination exceeds the threshold. So what we would then propose is estimates theta hat and delta hat, which are maximizers of the empirical true positive rate in the set where the empirical false positive rate is constrained. Now, the complication arises that in those sample means, we have indicator functions, which are not smooth. And so we can't really use derivative-based methods to optimize the true positive rate while constraining the false positive rate, which would be really nice if we could do. So we found smooth approximations to the indicator function that have been used a lot in things like AUC maximization. And these give us smooth approximations to the empirical true and false positive rate, where we've simply replaced the indicator functions on the previous slide with this smooth approximation based upon the standard normal CDF and some bandwidth indicator H, which I won't get into, but can be determined relatively easily. And in our simulations, it's the way that we've chosen it, it performs pretty well.
So just to make sure that I'm following you, essentially the actual entity that you want to estimate obviously is not available to you. You can only have the empirical estimate of what that value is. But furthermore, you don't actually have the analytical derivatives of what you're wanting for. So you can't just directly optimize it and move on with your day.
Yes. You could do something like a grid search, but for more than a couple of biomarkers, that's not feasible.
And because the dimensions just become too high?
Exactly, yeah.
Then does that smooth approximation actually then have a nice analytical solution? Or is it a smooth approximation that then leads to a nice computational solution?
Yeah, that's a great point. So it's smooth approximation that leads to a nice analytical solution. So we can actually, that's a good point. I could probably derive the gradients for these functions. I don't. We just use gradient-based methods to do that for us. That's the idea, is basically just making it computationally nicer for us.
Well, I'm totally with you on if you don't have to derive gradient.
Yes, I don't do that for fun in my spare time. So if we have a tool that can do it for us, we embrace that.
Very cool. And so just one other bit is that this, I guess, is it a hyperparameter H, where is that is affecting essentially the smoothness of your approximation? And do you need to tune that very well, or do things generally work out if H falls given range? Is it very sensitive?
It's not very sensitive. All you really need for the sort of asymptotics to go through is for H to be getting small with increasing sample size. And so that's basically, we propose using something that's based upon the standard deviation of the combination and the sample size as well. And so that sort of takes care of the sample size, the asymptotic requirement related to the sample size, and you can actually calculate it at the start of your optimization algorithm. You don't need to be updating it. It doesn't depend upon the values of theta and delta, essentially. So you just need to estimate it once, put it in, and then in our simulations and simulations that others have done, it works out very well.
Well, that is very good. So we've safely navigated around the Charybdis of analytical solutions and nasty math, and we're now smoothly sailing towards what we want.
Exactly. So essentially, yes, what we are proposing here is that if we maximize what we call the smooth approximation of the true positive rate, which is the TPR with the tilde over it, set where the smooth approximation of the false positive rate is constrained, that will give us the combination theta tilde sub t and delta and the threshold delta tilde sub t that we are looking for. And we have a theorem that under some conditions, we can show that the true false positive rate of that combination is constrained by t almost surely, and that the actual true positive rate of that combination and threshold and the true maximum of the true positive rate over the set omega t converges to zero almost surely. So it's basically saying that we have good operating characteristics of our combination theta tilde and delta tilde sub t. And then we have an R package with code to implement the method, because if you don't have an R package or you don't put the code on GitHub, then it's basically like it didn't happen. So we want people to use this, so we have an R package out there.
Yeah, if it's not in R and it's not in Python, it does not exist.
Exactly. You might as well not have done it. You can just shout it into the ether.
Cool. All the MATLAB listeners are like,
I know. Too bad.
Yeah. Cool.
So then I'll just touch on very brief simulation results. So these are a situation where the biomarkers, we have two biomarkers, X1 and X2. They are bivariate normal. So it's bivariate normal, but with some contamination with outliers. And this is based upon another paper that came out in 2017, their simulation scenario, which we found very useful in ours. And so here we have a true combination that's nonlinear, and we're going to construct a linear combination of X1 and X2. We have training data of 800 observations. We set the acceptable false positive rate to 0.2, so a 20% false positive rate. And then we have a very large test data set where we're evaluating these combinations. So the plots show the true positive rate results and the false positive rate results in that test set. So the little points are the means and the asterisks are the min and max, and then the bars are the middle 95% of the simulations. And we did 1,000 simulations, I should say. And so we compare our method to logistic regression, which is the GLM, robust logistic regression, which is in the blue, which is supposed to be robust to high influence points. And we see that our method offers gains in the true positive rate. And then looking at the false positive rate results, we have two results for our method, the STPR method, in green and purple. So the green is with a threshold estimated by our method, that delta tilde sub t, and then the purple is with it re-estimated based on the fitted combination. So the distinction between those is really minor and not of huge concern here. But the point is that our method did a fairly good job, particularly when we re-estimated the threshold, the purple, of constraining the false positive rate at the desired value of 0.2.
And just very quickly, the dots at the top and the bottom of each line, are those outliers or are those ranges? What are they?
So those are the min and max. Yeah, they're ranges.
Very cool. And I just have to ask, it's easy for me to ask this because I don't have to derive any of it. But as you know, there's certain methods like, for example, linear programming, where you can actually evaluate the sensitivity of your final answer with respect to the different constraints. Do you have some sort of ideas about how that constraint that you have, the FPR greater than 0.2, do you have some idea about how sort of sensitive your model is to that and how sensitive your outcome and your performance is to that?
Yeah, so here we have simulations with a false positive rate up to 0.2, but we do other simulations where we looked at false positive rates of 5%, 10%, and 20%. So we do have indications that our method performs fairly well under all those constraints. I would imagine that if the false positive rate was like 1% or less, unless you had a really big data set, I don't anticipate our method would necessarily perform very well. But outside of those very extreme cases, the indications from our simulations that the method performs well.
Cool. So it's sort of like, for some quick intuition, if you're moving that bar down, essentially you're going to converge more or less onto traditional logistic regression method because essentially you aren't constraining the model at all. Whereas if you bring it all the way up, essentially you're creating a joke model that only tells you precisely one thing because it can't risk any false positives.
Yeah, I would say so. Yeah, exactly. If your false positive rate constraint is almost zero, then yeah, nothing can save you at that point, really. Whereas, yeah, if you don't have a false positive rate constraint, then it's one, then yeah, our method would probably return something similar to logistic regression, is my guess.
Very cool. All right.
Okay, so then I just want to show a little example just to demonstrate that this is feasible in actual data. So this is just an application of our method to a study of diabetes in women with Pima Indian heritage, and this is just a data set that's available on R. So we looked at 7 biomarkers. We considered a maximum acceptable false positive rate of 10%. We split the data into training and test. So the training data had 332 observations with 109 diabetes cases. Test data had 200 observations with 68 diabetes cases. So you can see here the combinations estimated by logistic regression under GLM, robust logistic regression under RGLM, and then our method under STPR. And so the combinations are different. They are consistent directionally with the exception of skin fold thickness, but the magnitude of the coefficients definitely varies. And so then in terms of evaluating these combinations in the test data, we have true positive rates of 0.544 for both logistic regression methods and then 0.559 for our method, so slightly larger. And then we have a false positive rate of 0.18 for the logistic methods and then 0.258 for our method with the threshold estimated directly and then a little bit higher for the threshold re-estimated. So that indicates that the fact that the false positive rate was a little bit too low in the logistic regression methods and a little bit too high in our methods indicates that there were sort of important differences between the training and test data, which is not that surprising given that both data sets were small. So if our goal were to analyze this data set, I would probably do repeat sample splitting. For the sake of illustration, these are the results.
Very cool. And one thing I can't help but think of when I see your predictors listed out is there any consideration, for example, that we're trying to essentially minimize number of predictors or ensure that they're only combined in sort of
Reasonable ways.
you think about something strictly, a linear combination of two different features with different units doesn't really make sense. But obviously, correlation between entities does make sense. But I'm just a little bit curious, is there anything, because it seems like the methods that you're developing right now can sort of start bridging that gap to some of these other clinical considerations. And you seem like the right person to do it since you're already making clinical considerations.
Yeah. So first of all, you mentioned using these methods to sort of choose which biomarkers should be combined. And so one thing that's a possibility is combining these types of methods with penalization. So other people have done this for optimizing the AUC, so incorporating an L1 penalty, like a lasso type penalty, if you want to only include sort of a subset of the biomarkers, or a L2 ridge penalty if you think that a lot of the biomarkers should be in the model but with very small effect. So those types of considerations could easily be included in a method like this by simply adding a penalty term. And then as far as things having different units, yeah, so for the most part, and in this example, we standardize the predictors before the biomarkers before we put them in the model so that, the different coefficients, the different weightings kind of make more sense than if they were just put in raw. And so yeah, these are important considerations. And I would say the other thing is other people have looked into nonlinear combinations. We've limited ourselves here to looking at linear combinations, but I would say that there's definitely benefits looking at linear combinations. It's a lot easier for collaborators to understand what a linear combination is. It doesn't feel so much like a black box. It feels more defensible to them, I think, in a lot of ways, rather than some, crazy combination where you're looking at the square of number of pregnancies and the sign of plasma glucose. And so I think that there's a real benefit to keeping it relatively simple from sort of collaborative science point of view. But the flip side, of course, is that you might get improved performance from looking at nonlinear combinations. So this is the decision that we've made and the tech that we've taken in this paper, but certainly people are looking at nonlinear combinations for sure.
Yeah, definitely. It seems that especially if you want doctors to be happy with what you're doing, if better they can grasp it,
yes,
better.
I think no one really likes a black box, putting something in and getting something out, even if it's something you're getting something really good at. I think it makes people uneasy, most people.
Well, this seems like a very good solution until Cynthia Rudin saves us all from black box algorithms.
Yes, I hope so.
Very cool. Yeah, and just as another quick bit, obviously in defense of people using these nonlinear methods, the attraction to that is, of course, that, biological systems aren't linear. Knowing a patient, who all their problems can be solved by these dichotomized variables and things like that. At the same time, as you said, you don't want the sign of cubic pregnancies up into
Right.
the inflection point, at which point it becomes the quadratic of them or something like that.
That's exactly right. If you acknowledge that there's some strange nonlinear relationship between one of your biomarkers, or there's some interaction between two of your biomarkers, by all means, biological knowledge should definitely be incorporated. And to the degree that we know about it, it certainly exists. And so, so I think that's an excellent point, that information absolutely needs to be incorporated in situations where we have it.
I've really enjoyed talking to you. You're definitely working in a very cool clinical area. You're a person after my own heart when it comes to method design, tailoring your methods and your models very specifically to the clinical need, even if it creates further computational challenges that you must overcome. I'm further impressed, though, that you seem to have a stomach for analytical solutions that's far greater than mine. Thank you for fighting the good fight and also putting your work out on R where people can enjoy it.
Well, thank you for having me. It's been great.
All right, folks, well, that wraps it up for part 2 of Allison's episode. I think you can now really see why I was so excited to get everyone to listen to the projects that she's working on. Quick apologies as well for the drop in audio quality on my mic about halfway through this episode. A group of gentlemen charged through my backyard with about 7 leaf blowers, and I had to dash off to a different room, and so that changed the acoustics and warped the audio quality a bit on my part. Apologies for that. I'll try not to let it happen again. This also wraps up, so I really hope you guys enjoyed listening to myself, Emma Hughes, Greg Maislin, Martin Ho, and Allison Meisner. Coming up next week is our first episode of Season 1. We have Jerome Bergman and Daniel Moshe-Force, both from the University of Oxford, to come and talk to us about needs-led innovation. Again, I hope you enjoyed listening as much as I enjoyed recording each of these interviews, and we'll tune back in next week for the start of Season 1. Have a great day.
Well, that's it for this episode of the Pod of Asclepius. We hope you enjoyed it and will tune in for our next episode. If you're watching from YouTube, don't forget to subscribe to our channel and leave a like. You can also follow us on our other social media channels, including LinkedIn, Twitter, and Instagram. Have a great story or presentation that's ready for prime time? Or know someone who does? Drop Glenn an email because he'd be happy to hear from you. We would like to thank our sponsors from the American Statistical Association section on Statistical Learning and Data Science, section on Medical Devices and Diagnostics, and North Carolina chapter. The views expressed on the show are those of the speaker and not their employers, our sponsors, or anyone else not saying the words.